So acoustic emission is a method that I think is pretty neat, and it has a lot of potential for application in aerospace. And the reason there, we'll talk about the reasons for that and how it ties into it. But it's kind of a cool method. It's fairly new. What you'll notice as we get into it is that it is being acoustic. It shares a lot in common with ultrasound. It's almost you can almost look at it, for a long time it was almost considered a form of ultrasound, but now has been kind of separated out. So my clicker didn't want to work. So first of all, what is an acoustic emission? What are we talking about when we're looking at this? So the dictionary definition has to deal, or the legalese definition. I don't know what you would want to call it. So the generation of transient elastic waves produced by a sudden redistribution of stress in a material. And we've learned what transient elastic waves is a technical way of saying a sound wave. Okay, so we're looking again, acoustic should be that clue that this is sound by definition. So it's the generation of a sound wave produced by a sudden redistribution of stress in material. So redistribution of stress is a way of saying external loading of a material. So an external stimulus, something is applied to a material, whether that's a change in pressure, in load, and temperature, and it doesn't have to be the application, it can be a change. So it can be either the application or the removal of one of these things, the change in pressure, load, or temperature. And it causes, at some point, a release of energy, and that sends a stress wave. That sends a pulse, a wave of energy through the material. And so, when we did ultrasound, we sent a pulse of sound into a material and it traveled through it. And then we picked it back up. We sensed it using a piezoelectric transducer. And so acoustic emission is kind of like one half of that. It's rather than sending a sound wave specifically into a material and then allowing it to travel through the material and then sensing it when it returns to us, or if it doesn't return to us in some cases. Now the material, the sound itself comes from the material moving, or the material changing, some property of the material changing, and goes through, and then we can pick it up with a transducer. And some of them work in the ultrasound range, some of them work in other ranges. So it's different from ultrasound in that it's not strictly limited to those ultrasonic frequencies. It can be in lower frequencies than what would normally be considered ultrasonic. It can be more looking at the sound produced that's in the auditory range, something that you and I could hear. But it's sensed with the same thing. It's sensed with those same piezoelectric type crystals. So that wave of energy that travels through the material it vibrates that semiconductor in the piezoelectric sensor. That creates electrical pulses that then we can measure. We can look at different properties of them, frequency and amplitude, and we can then determine, or we can kind of get an idea of what's happening inside of a material. So it has some distinct advantages that none of the other techniques we've looked at so far have. And this is where it's really slick. I like acoustic emission. I think the idea behind it is really neat. And these advantages are kind of the biggest reason why. So first of all, this can be done on just about any material. And in fact, I have on there metals, fiber reinforced polymer matrix composites is what it's called officially, but fiberglass, carbon fiber and whatnot. But even things like concrete or wood, or one of the ones that you probably have all been familiar with, one of the oldest forms of acoustic emission is seismography. And so you've probably heard of a seismograph. When there's an earthquake, it's the plates of the earth shifting, and we pick up the vibrations from that. This is working on the same concept. Instead of large plates of the earth, tectonic plates, now we're looking at those pieces or sections of material moving within an object. And so, again, nearly any material, it can be earth, wood, concrete, or any of those things there. It can be a very fast method in that there may not be, in some cases where you have continuous monitoring, you don't have any kind of a setup necessarily. And so as aircraft, where this is really neat in aerospace, is as aircraft have become more computerized, as you have maintenance systems in them and you can drive more of that, these are systems, acoustic emission systems, can be installed in the aircraft and provide continuous monitoring throughout real-time use of the aircraft and the lifetime of the aircraft, as they can any other objects or equipment or whatnot that uses this method to monitor its health. So aircraft, it's becoming more common. Some of the earlier places it came about and where it was developed, a lot of it, transportation, has to deal with bridges. These systems are being deployed. In many cases, the United States has aging infrastructure. People talk about older bridges. And these sensors and data acquisition systems can be installed on infrastructure like bridges or buildings. In fact, these kind of systems, acoustic emission systems, were actually installed on the space shuttles before they were retired, after the Columbia space shuttle was damaged by insulating material hitting it on takeoff, on liftoff. And then it caused heat shield damage, which caused the shuttle's heat shields to fail on reentry at the end of the mission. They added these sensors to the space shuttle where now they could sense that impact. If they were able to, the idea was they could actually sense if an area got impacted by anything on takeoff, so they could understand if they needed to look for that kind of heat shield damage. So that fast, continuous real-time, what I mean by that is once the system's installed, it's there and you can monitor it constantly, and it can be done, it's all done by computer. This isn't a technique where you have to look at anything. It's not a technique where you have to physically measure anything. It's looking at a sound wave, and then algorithms are running on those sound waves to understand or have an idea what's happening. And so the data acquisition is real time and constant. The analysis then takes place real time and constantly. And it can be, and it's most often performed on objects in use. And by in use is, I mentioned a minute ago, right? We have to have external stimulus. Well, objects that are in use are constantly having some kind of external stimulus. In the case of aircraft, things like the wings and the fuselage and that, every time that aircraft lifts off, every time it moves, every time it hits turbulence, things are flexing and moving, right? So those are mechanical stimulus that are being applied to the aircraft. Bridges are every time a car or a truck or a vehicle drives over it, the space shuttle, that kind of thing. And so you don't even need to take objects out of service once the equipment's installed. If you're retrofitting something, you may have some downtime to install it. But once it's there and continuously working, you've gotten past that point. These systems, because they are remotely monitored and because they're sensing sound traveling through an object, just like ultrasonic testing, you don't necessarily need access to a specific location. So even if there's an area you're trying to sense, and I'm going to do some drawing just because I think it'll help to understand or help visualize a little better. So if we have an object, let's say we got our object, let's say it's maybe like a wing spar, right? There's our wing spar, okay? And here is, say the fuselage of the airplane. Yes, this is a awesome airplane. It's very aerodynamic. It's going to go this way. Okay, so we have our wing spar or part of the wing. Maybe that's the wing. I'll draw the actual spar here. Here's our wing spar, actually, you know, our front wing spar, kind of just behind the leading edge, right? And so that goes through the fuselage of the plane. So say, you know, normally we can't access, in the right color. Normally we can't access this area in here, okay? It's covered up, right? We got some, you know, so kind of some fairing area here. We might not be able to access this, right? This is inside the fuselage, okay? But the high stress point, you know, if we have a wing, our highest stress point typically is going to be right at the wing root. You know, probably right where this, oops, I want to draw, I don't want to move. Okay, well, right here, we'll say this darker dot on each side is the highest stress point, and we want to be able to monitor that. Well, what we can do is put sensors, and this is like a retrofit, but if this was being manufactured, you might be able to get to it anyways. But maybe you install, you know, you open a panel on the wing and you install a sensor here, and you install a sensor here, okay? And so now when the wing gets stressed, it gets flexed and moved, you know, if cracks start to occur and they release sound, it'll travel through this spar and we'll be able to sense it, you know, somewhere outside of that area. So that's what I mean. We don't need direct access when we do that. Okay? The other part of that is we need minimal preparation. And so, you know, in a lot of cases, these sensors or these objects are installed and they're left in place. And maybe, you know, there's a monitoring computer or something along those lines. But the other part of it is there are cases where, you know, if you do put this on for a period of time, a lot of times you don't have to worry about cleaning an area. You know, you just, you attach the spot sensors, and that's about the only area you need to clean. Most of the time you don't need to remove paint. You just have to make sure there's a good acoustic bond. And they'll use something to perform that acoustic bond, like a, you know, like the couplant gel we have. There's almost like epoxies that can do kind of the same sort of thing. So there, you pop these on. So, you know, we can put these systems on an airplane or, you know, again, a bridge or a building or, you know, any kind of object without having to cause much disruption in the ability to use that object. And once they're there, then we can perform that continuous monitoring and have fast real-time results. Now, there are some disadvantages, though, too. So the first is that the biggest one is that this is a dynamic process. And what that means is the material must actively be changing. And what we mean by changing is when you're applying that stress, it must cause some kind of change in the material and it must be a substantial enough change in the material that it produces what's called an acoustic event. So if you have something under stress and it has a crack in it that's growing very, very slowly, you're probably not going to be able to hear that. You won't hear, you know, that very, very slow growth, you know, and I'm talking about growth over days, over weeks, over years, you know, where it's very slow. It's not going to produce a single acoustic event that can be detected. So it needs to be a case where that stress is applied, and when that stress is applied, it causes something. And you can think of that, I don't know, I mean, you're all younger, but I'm not that much older. But, you know, someone stands up and you hear a pop, right? You hear a joint pop or a creak, right? Or you open or close a door, right? Think about a door. If you open a door, a lot of times you can open a door very slowly and it'll open and close quietly, but if you open or close it quickly, you get a squeak from your hinges. That's what I'm talking about here, where, you know, that slow, okay, open the door slowly, it doesn't creak, you can't hear it, you know, but if you open it faster at a normal speed, all of a sudden the hinges squeak and somebody across the room could hear what happened, could hear somebody walk in. That's kind of what's going on here. The other thing we got to keep in mind is that this is a qualitative process. Okay, it's very hard. There are scientists, there are kind of some cool studies where they are trying to get some more quantitative information, but for the most part, this is used as a qualitative measurement. So it's going to tell us damage has occurred or damage is present based on the size of the acoustic event or the parameters. What's the amplitude, essentially how loud it was, or how long it lasted, or at what frequency it is, you might be able to have some kind of an estimate of the amount of damage or the amount of reaction that took place. But it's not going to give you a very definitive quantitative size, depth, that kind of thing. So acoustic emission is also, or is often used in collaboration with something else. Okay, so we put these sensors on an airplane, we put them on a space shuttle, we put them on a bridge, and we get, a signal that an acoustic, something has occurred, a flaw has occurred that created an acoustic event. Now that's a signal saying, hey, we need to look at it closer. And it might give you a general idea of where it is, especially there are techniques where you put multiple sensors around and you can kind of triangulate, based on how loud it was at different sensors. Multiple sensors pick it up, and they're going to pick up that same event at slightly different times because the sound has to travel. They're going to pick it up at different amplitudes because of attenuation, sound traveling. And so it can kind of give us a general idea of the location, possibly the size, but then we're going to have to go in and probably use another technique to perform measurement. And it could be ultrasound. It could be eddy current, it could be dye penetrant, it could be mag particle. So it's qualitative only, and then we often have to use a second technique to perform a quantitative measurement of what's happening. The other thing we run into is it's sensitive to extraneous noise. Okay, so the truck rolling over the bridge is going to stress the bridge. It's going to cause it to bend and flex and move. At the same time, the wheels of the truck running over the bridge are going to create a lot of noise. They're very loud and vibration and that kind of thing. And so we have to be aware of that. Now, that can work to our advantage. There are cases where acoustic emission is the bridge or the wing or the spar or whatever giving off a sound. You can actually sense how a sound transfers through something too, but it's almost going into more of an ultrasonic type. So that wheel noise, if there's damage that occurs, that wheel noise of the truck may change as well. Okay, so it can be used in that way where you look at that traveling through. But for the most part, that kind of thing is going to be background noise or noise that can cause issues, extraneous noise. So what are we looking at? The general theory is that the emissions are the result of the initiation or growth of things that are known as cracks. So we all know what cracks are. We know what a slip is shown here in the diagram, what's called a slip plane. This is where the atoms get displaced from one another. It's a shear, it's kind of a shear force, okay? Same thing with dislocation. Now, twinning is one you probably haven't heard of, but if you've heard of plastic, there's different kinds of deformation. You have elastic, that's where something bends, but it goes back to the shape it was in. And then you have plastic deformation. You bend something and it stays bent, but it doesn't crack or break. And then you have your failure point where you actually get something to crack or break, kind of your three levels of deformation. And so twinning is primarily that plastic deformation. Okay, slip is a form of actually causes a tear or a crack or a shear in the material. Twinning is where it's that same, it's kind of before the slip actually occurs. You kind of get that turn happening. The last one is phase transformation. And I don't know if anyone here has spent time around like a lake in the winter, that kind of thing, but you'll hear lakes, you'll hear the ice groan and pop and crack, and that's acoustic emissions coming from the freezing and thawing. Or actually, probably the best one, your car, you drive your car, you park it, and you can hear your exhaust system making the pinging noises as it cools down. Another form of that's that heat and kind of movement. It's not a true phase transformation because it's not going from liquid to solid, but it's caused by that heat stress. And so again, like I said, it can be a removal or application of stress. A lot of people think it's just the application, but a lot of times the removal can also cause it. And they are elastic waves. So just understand the actual waves. So this slip is a plastic slip and twinning. These are plastic or destructive, their plastic deformation to start, right? Things are actually moving. The ultrasound waves themselves are elastic, right? The sound, we're not putting sound in that actually causes things to break. The cartoons are famous for doing the opera singer with the glass, and she sings really loud and high pitch, and it shatters. Okay, that would be a non-elastic wave. That would cause plastic or permanent deformation. But your elastic sound waves, your normal sound waves, don't cause any kind of deformation. It's just the movement of the atoms back and forth. But everything, when the sound goes away, returns back where it is. So that's what we're looking at with the sensors to detect these permanent non-elastic flaws. And so then those waves are detected and analyzed, like I mentioned. So when we look at the wave, we got to keep some things in mind for what it is. So down here on the right is what's called an acoustic event. Okay. And so whenever we're working with acoustic signals, I'm going to jump down to kind of the third bullet point here. And I'm going to talk about threshold first. So when we have these, when we're looking at any kind of sound that's coming from an object or transferring through an object, we need to decide what is an acoustic emission, or what is a relevant acoustic emission versus what is just that background noise, or what do we not care about. And so that's what the threshold is. So a minimum signal strength, what we're showing here, is the amplitude. Here's the 0 point. And I have voltage because this is the signal. This is you have the sound wave is hitting the piezoelectric crystal. The piezoelectric crystal is creating an alternating current voltage. And so this is the voltage, which is basically it's directly related to the sound wave as well. A piezoelectric crystal is taking that sound wave, that acoustic wave, and transforming it into an AC signal that basically looks the same if you can put them kind of in an oscilloscope. I mean, that's what a microphone hooked up to an oscilloscope is going to do. And so this can be voltage, or the amplitude. It's the amplitude of the sound wave, which corresponds directly to the voltage. So we have our 0 point, and the wave starts to go up and down, and they've kind of got two things here. You got your solid as the actual wave, and then they've also done the positive half wave where they've flipped each of these negative things, right? Just to give you an idea of the total amplitude. And so the threshold is how big of an amplitude of a wave do we need before we consider it interesting? Before it's not just background noise, or before it's not just the normal kind of hum of something. And so when we get a burst of a signal, a set of a waveform where it is exceeding that threshold for a period of time, we call it a useful signal, a transient signal, or a burst signal. Okay, and that's what we're going to then analyze to try to figure out what is it telling us. Okay. So what happens here is when we're looking at the transient signal, the normal, you're used to a sound wave having amplitude, and you can see this wave, this energy pulse, has a changing amplitude. So when we're looking at a single event, the ultimate amplitude is basically that highest peak. Of this whole event, what's the highest peak? And so that gives us the amplitude of the burst signal. Okay, but that doesn't tell us everything. You can see there's a lot before that. There's a little bit before that. There's a lot after that. And that, analysis of that can be just as important as the overall amplitude of the signal itself. And so that was, so we've got that threshold. We went above that threshold. This is the peak, but we can look at how quickly that peak came, which is known as the rise time. So that's the time going from the very first location, or the very first time that that our signal crossed our threshold, which is right here. Okay, you can see our signal crosses the threshold for the first time there, to its max amplitude, or to the amplitude point. Gives us that rise time. Okay, and that can be, typically that's very quick, especially when we're looking at, you know, these quick applications of a stress. It can be very quick. It usually doesn't ramp up, but then it causes, there's a lot of residual vibration after that. That's this tail off to the right. Okay, so you've got the total duration, which is where, you know, we first start to go away from the center point until the last cross, sorry, from the first cross of the threshold to the last cross of the threshold is your total duration. But that can be split into the rise time and then, you know, basically the duration minus the rise time. And so these are also very important when we're looking at the analysis. So it's not just the amplitude, it's not just how loud it is, but it was how long did it last? How severe? And these can be directly affected by the that material reacting and that quick event, and understanding what just happened inside the material. Are all of these. Obviously, the larger the amplitude, or the larger the damage, or the larger the crack, the primary thing it's going to do is increase the amplitude. But based on how quickly, you know, it's not a crack or a break or something, it's not an instantaneous event, right? It sounds to us, we perceive it, people perceive it as a near instantaneous event. But it's not instantaneous, and so that's going to affect these times, and that's where, you know, these two things together are going to be important. And then the frequency along with that, if we look at the frequency and that duration, we can get what's called a count, and that's how many times the signal peaks above our threshold for a single event. Okay, so in this case, this has 8 peaks, you know, from here to here, right? You can see lines up with this pulse. And from here to here lines up with the second pulse. And from here to here lines up with the third pulse. And so on. So this has this very last pulse, this small, you know, the small peak right here is our 8th pulse. So the counts are not based on a time given by the machinery or by the tester, but the time, they're in the time it takes for that signal to show up until the time that signal goes away. And so, you know, using all these different areas, we're able to do that. There are also a lot of times, and I don't have it on here, but oh shoot, I want to say it's called MARSE, M-A-R-S-E. Looks at another thing that you'll see is, let me clear my things. They'll also commonly look at the area underneath this curve. So looking at the area underneath here. Oops. Round over. That's really bad. But so the area inside of my red line there is MARSE, and that's also looked at. That's the total energy that was released, or that was the total energy that was sensed by the sensor. It's not the total energy released, because some of the energy is going to be picked up by the sensor. Most of the energy is going to go off into other directions. But the total energy picked up by the sensor is shown under that area underneath that outline. And that can give us an idea of how much energy was released overall from the damage. Okay. So let's go ahead. I'm going to stop here.